Teragamma motor control provides a powerful tool, the flexible optimizer, to support motion control optimization. It automates what it does best, so you can do what you do best.
Hi, I'm Chris Cullen of Teragamma Motor Control. In this video, I'm going to show you the flexible optimizer, automation that helps you search for the best parameters to optimize your servo motion. It can be used for closed-loop control tuning, as well as optimizing feed-forward and motion planning. The flexible optimizer is halfway between the completely autonomous Teragamma self-commissioning and the manual process supported by most servo vendors.
I'll show an example, changing the load on an axis. This demonstration axis is commissioned automatically using Teragamma technology. It uses this 1.2 kilogram test load. The load-to-motor inertia ratio is about 3.2. Commissioning couldn't be simpler. You enter 4 numbers, and press Start. In about 5 minutes, self-commissioning identifies models of the motor and axis and designs closed-loop controllers. Usually, these provide near-optimal motion, and little or no modification is needed. Let's look at the step and settle performance, which is usually excellent. We'll load a motion script of 10 steps, 5 forward and 5 back, 1 motor revolution each. The planned motion time is 22.3 milliseconds. We can see that in this normalized plot of all 10 steps laid on top of each other. The planned motion you can see is 22.3 milliseconds, and all 10 motions have entered the 5 encoder count in position band in 1.6 milliseconds, settling to 1 encoder count at the latest 9.2 milliseconds.
What do you do, however, if you now want to move a much smaller load? Here, we're changing the load from 1.2 kilograms to 0.2 kilograms by removing both of these weights.
Let's see the performance we get without any modification to the motor configuration. We'll run the same script again. Same planned motion time, no surprise. Settling time is shorter. Let's have a look. Here we can see that it settles to 5 counts in 800 microseconds, settling to 1 count in 7.7 milliseconds. We expect that a good position controller is robust to variations in load, and this one is. The planned motion time hasn't changed because the model hasn't changed. The motion planner computes the motion parameters, velocities, accelerations, and jerks, so that the available voltage and current is actually used. Also, feed forward is based on the model, which reflects the old heavy load, and so tracking error is also probably larger than it needs to be. We'd like to optimize to reduce planned motion time, tracking error, and settling time. Here's the traditional way. First, pick a stimulus. We can use our 10-step script. Now decide on a metric that you'll use to judge performance. For example, integrated absolute error during settling and constant position command phases. Now decide what you're going to vary. For a closed-loop controller, you could vary bandwidth, or damping, or patience, although many vendors only support bandwidth. Let's play with damping. So now you'll start to optimize. Let's try running the script. And we have a value for our metric. Now we can play around with damping a little bit. We make a little variation. Try again. Notice that the metric isn't the same with every trial. That complicates things. Pretty soon, you'll find that you need a pencil and paper or a spreadsheet and graphing software to keep track of your trial values and the metric values to try and find your minimum. After a while, many engineers will find a rough value and say, that looks good enough. Teragamma provides a simple, high-level approach. Simply repeat self-commissioning. In this case, however, we only want to relearn the load, and so the process can be greatly accelerated by using the advanced options and checking the Use Existing Axis option. This keeps existing electrical and thermal models, but identifies a new mechanical model and designs new controllers. The Teragamma Flexible Optimizer takes some of the best features of self-commissioning, but offers you more control. Let's see how this works. To perform an optimization, you need to choose 3 items: a stimulus, a performance metric, and the parameter set to vary. We'll start by optimizing the mechanical model, which is used for both feed-forward and motion planning. We'll start with a course search, feed-forward course. This systematically varies 3 model parameters, including inertia. For feed-forward, the best stimulus smoothly varies acceleration and velocity over a wide range. Therefore, we want a contouring type motion. You can write a script for your own axis, and this may be the right thing to do for special application requirements. Teragamma also provides other useful stimulus options. We'll choose Make Contour from this pop-up menu. This is not a constant script. The motion is recomputed each time the model changes, so if the inertia is less, acceleration will be greater. This allows identification of the model to be more accurate by using the full range of feasible accelerations and velocities. We'll choose RMS error for the performance metric. This is appropriate for a continuous tracking stimulus. We can execute the motion without running the optimizer. And we'll go and look at the RMS position error, 7.46 counts. You start the optimizer by checking this Enable box. You can run the trials one by one and see the results of each trial. But why do that? Let's enable script cycling and let the entire search happen automatically. Here we go. That didn't take long, did it? The RMS position error went from 7.41 counts to 3.21. Now we'll do a fine search to get all the parameters to their best possible value. This is a 5-dimensional search. It varies 5 model parameters over a smaller range. We enable the search and start. That didn't take long as well. It reduced the position error from 3.3 to 2.27 counts. In less than a minute, we've reduced the RMS position error from 7.41 counts to 2.27, almost a 70% improvement. Let's see the effect this has on our 10-step motion script. We'll reload the script, run it only one time, and run it. The planned motion time has gone from 22.3 milliseconds to 20.9. That's because the motor was not working to its full capacity, and now it is. This 1-minute optimization has not only improved tracking error dramatically, it's also reduced planned motion time by 6.3%. Now we'll see how to tune closed-loop controllers. Let's use it to find the optimum level of damping in the regulator. Open the control window and select the regulator. The controller you display in the control window is the one that's modified. Now select Damping to search on. For the performance metric, we'll use still IAE, Integrated Absolute Error. And this is only computed during the constant position command phase. We'll show damping in the control window so that we can watch the progress of the search as it proceeds. For stimulus, let's use a step and settle motion, but we'll only do 4 steps to save search time. You can see the dwell time is 50 milliseconds, and each step is 1 motor revolution. Okay, now we run the optimizer. Enable control, cycle the script, and begin. The search pattern is tailored to each parameter. You can see that for damping, the search is outward in either direction from the starting value. This helps to ensure that an interval of good results are found in case instability limits the trials at very low or very high damping. And now we're done. That took about a minute. And we can see that the flexible optimizer found the best value of damping at 42.4%.
The flexible optimizer works with external motion generation as well. We'll plug the motion controller pulse direction output to the Teragamma drive's second encoder input.
We've already configured encoder following using the tracking window. Type, filter, etc. all have automatic learning support. We use Teragamma to compute the optimal acceleration that we then programmed into the motion controller. We'll go back to our first optimization example, course feed forward, RMS error. This time we make sure that all external motion is recorded. For external motion, the dwell time is set by the post-motion recording time, and we'll use 50 milliseconds. We want steps in each direction for each trial for better accuracy, so we'll enter 2 moves per trial and command a series of back and forth moves. Okay, let's get started. We enable the servo, enable optimization, and start tracking. Now we command motion externally, forward and back. And here's the first trial. Forward and back. And there's the second trial. The process is driven by motion controller moves, but otherwise the flexible optimization process is exactly the same as for internal motion.
You've just seen a brief overview of the Teragamma Flexible Optimizer. I think you'll agree that it sets a new standard for ease of use in the tuning and adjusting of servo motion performance. Thanks for watching.